Hello everyone. Welcome to the week 7 discussions of the course Fundamentals of Micro and Nanofabrication. So, I am Uditya, PMRF scholar from IIT Madras, and we will be going directly to the problems solving session to the of week 7. So, this week's focus was on optical lithography. So, we went we discussed in detail the different types of optical lithography. The first lecture was on contact and proximity. Basically, it's the distance between the like depending on the distance of the mask from the photoresist. We classify the optical lithography into different types, and one of them is contact, another is proximity, and on and then we have some two systems on stepper and scanner, and also the other type, that is projection lithography, in which we use projection optics uh, for for doing optical lithography. And so the first video of projection lithography was on how the image is formed, and so it was on the overall video, but it is on how the fourth video discusses in detail how the image is formed on the photoresist and what are the contrast issues and all the things that we discussed here on the photoresist. And the third one is in the last video is in the surface reflection. So how the light is reflecting from the different interfaces, the silicon interface, the photoresist interface, uh, and how that reflected light can affect the surface features, the features you want to have on your wafer, how it can affect that thing. So that we discussed in the last video. So okay, so this is the problem one. So this is a question from projection lithography. So in projection lithography, we have two kinds of system. Another one is stepper, and another one is scanner. So you have to mention which one of them, stepper is better in what terms compared to scanner. So these are the options, and you can. So, so you have to compare basically stepper and scanner, and you have to mention which one of the properties you find in stepper in compared to scanner. So if you have any issues with the understanding the question, you can ask, uh, and you can write what you think the answer would be, and we can discuss. So by resolution you mean the ability to distinguish two features. So if you have a low resolution, you can distinguish uh, very small features. By throughput you mean like you can scale up that process like to multi-scale. So scaling up is easier, so we say that as throughput. And uniformity means the uniform patterning of all the patterns, and so that's all the option means. Okay. So yeah, you are correct that throughput is the correct one, because in scanner we have a slit. So we have like this is the slit which is present between the between the like the light projection system and the photoresist. So what happens is that this 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 slit is moved. This essentially this slit is scanned throughout the mask pattern, and this is done such that a uniform illumination is present at that slit. That full slit is illuminated uniformly. So that's the thing. So yeah, so the thing is throughput is the thing that is in favor of stepper. Other things like resolution and uniformity is something that is kind of achieved better in scanner systems. Okay, so you'll move to the next one. So this is a numerical. I hope you will have calculators or like a mobile. You can use them. So this question is from proximity printing. Uh, so here it is given that two wavelength filters were used. One was lambda 1 was 195 nanometer and lambda 2 which is unknown. And the gap between the mask and substrate was fixed. The best resolution that was found with lambda 1 is 500 nanometer, and with the lambda 2 it is 684 nanometer. So you have to tell the value of lambda 2 in nanometer. So you can think like how in proximity printing uh, uh, like how resolution is depict like how what resolution depends in proximity printing, and that's how you can approach. So that way you would be able to solve the question. So I'll give you some time and you can try, and then we will discuss. I hope like you can recall the relations, yeah, the relation between the resolution and other factors, like what is the factors that the resolution in proximity printing depends upon. I hope it is you can recall them. Okay, so we will go to the solution then. Yeah, 361. Okay, let's see. I also do not know the answer. I would have to also solve the thing. Okay, let's see. So essentially, what is given is so the relation. First, the relation is the resolution is related to lambda and the gap between uh, the the mask and the substrate. Yeah. So lambda root over lambda by lambda into g. So the thing is, we can write that lambda 1 equal to w1 equal to root over lambda 1 into g, and w2 equal to, yeah, because the gap is same. So dividing the both the equation is root over lambda 1 lambda 2 g g. The g is cancelled because the same. So lambda, the resolution of first one is 500, and the second one is 684. One is 195, and this is 100. So essentially 500. Okay, so 500 divided by 684 is coming to be 0.731, 195 lambda 2, and so lambda 2 equal to 195 divided by it's 0.731 square, that is 0.5334. So yeah, it's coming for me it's coming 365 .1 360. Yeah, I hope you did it this way. Yeah, you are okay. Okay, okay. So yeah, that's the answer. Some might be some you might have got some closely related because you might have taken some approximation. So yeah, that like something 361 to 366 I think is okayish. That range is okay. Okay. So we'll go to the next one. So this is also numerical. So the source wavelength is given, and it is a normal incidence. So and the periodic pitch is 1 micron, and so we have to tell what is the angle theta, which denotes the second order of diffraction. So this is a lithograph system, and you have this periodic structures, and you have to tell in at what angle the diffraction of second order will be visible. This theta. This theta. If you have any doubts on the question, you can ask you. So like you have to think towards like how uh, this ordered this angle and how this ordered diffraction patterns are related. So that way you can tell. This 29.7 degree. Okay, let's see. I also, yeah, I also don't. Let's solve it. So, okay, it's given that lambda 1 equal to 248 and p equal to 1 micron. So, 1 micron is 1000 nanometer, yeah. So, so essentially, the relation is sine theta equal to n into lambda by p. So here n is the order, lambda is the wavelength, and p is the pitch. That is 1 micron. So we have to put as 2, lambda is 248, and 1 micron I have to convert, and it will be 1000. So essentially this is the thing. 248, 496. This comes at 496, and so theta equal to sine inverse 0.496. Yeah, 29.7. Yeah, perfect. So yeah, perfect. So we'll go to the next one. So this is the continuation of that question only. So you have to tell what should be the numerical aperture of the lens, and you have refractive index, like you are the other details remain same, and the thing is you have to find the refractive index of the lens, and it is immersed in oil of refractive index of 1.33, and you have to capture uh, the third order. So last time we were capturing the second order, so here you have to capture the third order. So like when we increase the numerical aperture, we can capture the higher orders of diffraction also, yeah. So for that you have to like tell what should be the numerical aperture, and it is in the it is in the environment, like the refractive index you can tell, you can take as the as oil of 1.33. So are you able to do it? Okay, let's discuss, no issue. So we know that the sine theta equals to n into lambda by p. So here we have to capture the third one. So 3 into 248 into 1000. So same thing, we will find the theta first. Yeah. So it will come at 7 point. So after that we know that numerical aperture is equal to n sine theta. So here n is given, and this is the sine theta. So you will get 0.98. So this is the numerical aperture of the lens. Yeah, sure. Yeah, like uh, that's resolution. How like by how the resolution, you are asking that how the resolution will improve when the numerical aperture is changed by introducing oil. So the thing is how that light is moving in what environment, like you know that that wavelengths, how they will change, like depending, like we like whenever like we have a glass here, and we have air here. So the wavelength here and wavelength inside the glass will be different. Yeah. Essentially, the wavelength inside the glass will be lambda by numerical aperture. Okay, and so the thing is how it will improve. The question is how the resolution will improve when n is changed. So that's why the numerical aperture is something that defines how much of the light that is captured by our lens. So you will have bigger lens, then you will have you will capture more light, yeah, more orders of diffraction patterns. So that's why by that you will increase the, like, that's how the thing is, na? Like, yeah, the numerical aperture is directly like directly proportional to the uh, your uh, the refractive when the wavelength changes, the effective wavelength changes. So the acceptance, yeah, how to quantify. So uh, the, like, you have to, okay, so that thing is like you have to tell how much is the the resolution, yeah, resolution of the system. I think So I hope you are asking that resolution of the system, yeah, like any lens or something. That sort of. So resolution is they say it is lambda by 2 by numerical aperture. So when in microscopes, when you have this thing, uh, like when we decrease the numerical aperture, we have higher resolutions. Resolution of the pattern. Yeah, that's the same thing. Yeah, it's the same thing. So like you will go for higher resolution. So you will have bigger patterns. Yeah, you can't resolute to less pattern, so you increase the resolution. You want to have, for like ideal system, you want very low resolutions. So that's the thing, the aim is towards getting lower resolutions, like lower in a sense ki you want like you have nanometer scale and you have micrometer scale. So nanometer one is more high resolution, and this is less resolutions. Like this will have very less patterns, you can differentiate very less patterns. So that's how, because the thing is, with higher numerical apertures you are gathering more orders of light, so we'll get more features. That's the thing. But then you will get there's some give and take also, like with more numerical aperture you will have higher optical path difference, so you can only have very less working distance. So such kind of things are there, but essentially for resolution you can go for higher numerical apertures. That would be good for getting a very precise or very small patterns. Hmm. Okay. When we change the effective wavelength and yeah, like such things are there, but like that is something like how much that thing is changing, and what that photoresist is absorbing. Yeah, such things are like uh, essentially that is something that is taken up with the like quality factor. Yeah, like how that is like some tolerance is there, that is there, and we see that they don't like it is like that only, like how much it is like what changes these patterns this lens are getting, that doesn't change such kind of things, that it will not there will be a vast difference between the transmission or absorption properties. That's the thing. So that is there. So they take that in like consideration. Okay, so we'll go to the next one. So after some numericals, this is a short question. So how many diffraction orders are at least required to form an image? So okay. So actually it's uh, two two orders, two two diffraction orders are actually required actually, such that we get a interference pattern on like one pattern is this one and other one is the other one. So you have to get at least two orders to have a image formed on the photoresist. That's why we will at least get this. We will at least have systems that can at least like cover the second order. Okay, and if you go for more orders, you can get more higher resolution also. That's the, like that we discussed last question. Okay, cool. So next one. So this is also a numerical, a partial theoretical also. So you have E1 given, the E1 is exposure dose, and E2. So E1 you will find here, E2 here, and you have to find the critical modulation transfer function, and you also have to tell what is a positive or negative. Is it a positive or negative resistor? So feel free to answer, and we'll discuss.
Do you have this?
So first you can tell what kind of photoresist you think it is. I think that will like narrow down the options, and then we can.
Burger, you put it 50 rupees each, it seems. Rough value. Okay.
Okay, positive. Okay. The critical modulation transfer function. So this critical modulation transfer function is something that is one of the factor that helps us to understand the contrast of the. Although there is something called resist contrast, but this is also a factor that can help us know the function, like how the contrast is varying with the dose. Yeah. So essentially it is it is kind of same only. That so you have to I think you are telling about that's the same, the things are, you can take that's something like a term.
653, right? 18. Okay, 18.
So the thing is, we consider CM, TF or anything MTF total. We consider the energies, yeah. We see the higher energy, we see the lower energy, and we find essentially this. And you can depict it in different terms like I2 minus I1, I2 plus I1. Yeah, I hope that's the thing you are telling. Some people might write it like D2 or D1 dosage. Okay. Okay. So can you okay, can you tell why it is photoresist? Why is it positive
300
photoresist?
rupees
Why
for
you think so?
plate. MS plate. Here bracket. 300 rupees.
Yeah, true.
This is converted
So as you said, it is like with higher energies, it is getting removed. So yeah, perfect. That's why it is a positive resist. So we have only two options. So the module so the critical modulation transfer function is essentially the like so we have to see where the energy is like how it is how it behaves at the 100% exposure and like when it is 100% there and when it is the lowest. So you have to see the like the dosage of energy. So here it is E2. So when it is the resist remaining is 0%. Yeah, and this is when it is 100%. So and this is essentially the same. And I think these are mentioned in different terms. I think in lecture it is mentioned in I think this format. Essentially, we can see that E2 is what it is 200 minus 100 and okay. Anything intensity also it's kind of yeah, same thing. 150 plus 200. So yeah, 0.143. This is the correct one. Okay. So okay. So this is also the continuation of that question only. So you have to now find the resist contrast of the photoresist. So this is also a term that is sometimes that also is taken in consideration when you have to understand how the resist is behaving with the exposed light. So actually this was something that we had dealt with in the last week's videos. So I think there you have found this. So just if you can recall, that's good. But anyway. But this was I think mentioned in the last week's thing. But I thought that's something. Okay, resist contrast is something that how it changes with the energy. So like basically we want what we want something to be boxy kind of, yeah. So that contrast how it is like with high energy and low energy. So that contrast is something that we tell as resist contrast, but that has some formula actually. So this slope is something uh, that matters. Yeah, we essentially have to like essentially this slope needs to be it's more yeah, no issue. Can't No issue with that. So it's basically we want a steeper profile like this, and whenever this thing is it is like this, so it had you can say it has less contrast than this. So if you have 1, you have 2. So this have lower resist contrast than this. So that's the resist contrast. So we want that thing, how boxy it is. That's the thing. So okay, no issue with the formula. That's something that you can. So resist contrast. It is essentially the log 1 by log of E2 by E1. So you can 1 by log
ఎక్కడ అది కాదు నువ్వు
0.125.
ఓకే అంటే ఇక సైకిల్ మీద అంటే సరిగా ఉన్నావు
8. So you can maybe just go to that lecture and that might help you get the thing, recollect the things. Yeah, like how the things are derived and how we end up in this.
So you can go directly and just because they don't know that much guidance. Later then you can go from there. Go to the health money with you. So I will share you the most favorite photo. Okay.
So this is problem 8. So it's about the anti-reflective top anti-reflective coating layer, which is used over photoresist of refractive index. So refractive index of photoresist is given 1.9, and to reduce reflection, so the wavelength of the source is 248 nanometer, and we have to tell what should be the optical thickness. So optical thickness is the product of the refractive index of okay, yeah, essentially yes, you can tell, because that's the slope would be something that is. So and you end up actually discussing how that slope would behave, and that's how you will get it. Okay, so coming back to this thing, so this is the product of the refractive index of the top anti-reflective coating and the thickness of the so it should be the optical thickness of the for lowest reflection, and what is the optical physical thickness of the top anti-reflective coating. So you can try. So essentially what is given is n of PR 1.9 and lambda 248. So you have to find n TARC and T TARC. So this is a question from the last video of this week's course. So essentially, this top anti-reflective coating is used, and this basically adds optical difference, and that's how we get a kind of say a profile that is changing with the D. Okay. Yes, we will solve it then. Okay, so NTARC is related to NPR. Yeah. So NPR is 1.9. So under root 1.9 is 1.38. Okay. So and TARC thickness, you would get lambda by 4 into NTARC. So let's lambda by 4 into 1.38 45. Okay, 45, and so we have to multiply 1.38 into 45 is something, yeah. So D is the correct one. Okay, very good. So we'll go to the next one. I think that's the last one. So this is simple theoretical question. So you have to, it is a multiple choice, so you have to choose whatever options seems correct to you.
Comments make it bigger.
Okay.
Wait, I'll tell you. Comments.
So you think only one correct? So you think only one is correct? Other options? Okay. So essentially, standing waves, removing standing waves is okay. That's yeah. C. Okay. Okay. Let's discuss them. So removing standing waves. So essentially, when we don't use this ARCs, these uh, like waves can interfere together and form uh, standing waves in the towards the not signal.
Only one case we can confirm.
With the in the photoresist, yeah. So essentially, you have to remove standing waves. So that is something that helps in, and this anti-reflective coating can help in it. Increasing depth of focus, so it's not something that can it is not used for increasing depth of focus. So improving resolution by decreasing the refraction, it's also not there. Essentially, it is like uh, it increases essentially. It like you can see refraction when it happens when you have this refractive index n1 and n2 is there. So essentially n1 so refraction actually increases, and here I think with resolution is not something that is we are shifting, we are saying here, and introducing a pi phase shift. So essentially this pi phase shift is something that is introduced, and that only helps in having a destructive interference such that we get a clean profile on the photoresist. So that's how so this is the reason that this standing waves is removed. So essentially these are the correct options, A and D. Okay, so with that we can close the session today. I hope you got the things. Okay, thank you all, and have a nice day. So if you have any doubts you can stay back, otherwise you are free to leave. We will meet in the next time, same next week, so same time, with week 8 videos, discussions on week 8 videos problem. So thanks a lot for coming.